Hello and welcome to Edunguru students. Till now we have studied about vectors, we learned kinematics, then we saw particle dynamics. In particle dynamics we discussed about laws of motion, friction and circular motion. Now let's move ahead to the new chapter, work, energy and power. It's a very important chapter and the concepts of work, energy and power, you will see that it will be applied mostly in all the chapters, right? So let's discuss work, energy and power. My first question is, what is work?
Sir, may I?
Yes, Adamya?
Work is force multiplied by displacement.
Good. So work is a product of force and displacement. Now this is what you guys are aware of, but according to me or according to physics, there is a catch in it. Work is given as F dot S vector. We are assuming that the force is a constant. Now work is equal to F dot S vector, given as, it can be further written as Fs cos theta, where theta is the angle between F and S. What is F? F is the force, because of which we want to calculate the work done, right? What is S? More precisely, I will write it as the displacement of the point of application of force. Now what does this S cos theta represents now? This S cos theta is displacement of point of application of force along the direction of force. This is what is work done. So I rewrite it. Work done is given as Fs cos theta, and this is S cos theta is the displacement of point of application of force along the direction of force, and F is the applied force. So work done is the product of the applied force and the displacement of the point of application of force along the direction of force. Now I'll try to explain it to you. If you keep on pushing a wall, after some time you'll get tired, right? Now, have you done any work? Obviously not. You lost energy, but that energy is not transformed into the displacement of the particle. It is not transferred to the second object. The wall it remains where it was, but you are tired. So according to physics, you haven't done any work. So please remember, work will be done only when there is a displacement of the point of application of force along the direction of force. So please remember it. Let's try to see one example. This is a block of mass m and a force F is applied along a direction making an angle theta with the horizontal. So this is force F. Now the horizontal component of this force is F cos theta. This is the point of application of this force, right? The vertical component of this force is F sine theta. Now, when I push this block in the forward direction, this is the new position of this block. You can see that the point of application of force is displaced from point A to point B. This is the displacement of point of application of force. Now, if I ask you to find the component of this displacement S vector along the direction of force F, this is the direction of force F. The component of this displacement along the direction of force F will be given like this. Please look at the green line. This is the displacement of point of application of force F along the direction of force, of course. So this is, if this length is S, then this length is S cos theta. So the work done here is F S cos theta. We can also write it as F cos theta into S. And what is F cos theta representing? It is representing the projection of force along S vector, right? So this is work done. Now, since it is represented by a dot product, therefore work is a scalar quantity. Its unit is in, it is measured in its SI unit as joules, denoted as capital J. In CGS unit, it is calories, right? This was the work done by the constant force. Now let's learn work done by a variable force. Let's take one more example. Suppose this is a block. It is kept on this surface. Initially, the block is at some location, say x is equal to A. We apply a force on the block. The force is, which is equal to A plus Bx, is acting on the block. Now you can see that the force is a variable force here. The force is changing with position x. That is why the force is a variable force, right? Now we will try to find the work done by this force. This force is pulling this block from x is equal to A to x is equal to B. There is an intermediary position of this block at some x is equal to x. What we will do is, we will find the work done by this force for a very small displacement dx, because the displacement is along x-axis, right? So let's see, this is a small displacement of this block. This is the small displacement of this block along x-axis. So this is dx vector, and this is the force vector F. Now, the work done for this small displacement is F dot dx. We assume that for this small displacement, force capital F is not changing. So we have dW is equal to F into dx, because the angle between F and dx is 0 degrees. The value of capital F is A plus bx multiplied by dx. Now, we have found work done for a small displacement by this capital force F, and this is A plus bx into dx. To find total work done during the displacement x is equal to A to x is equal to B, what we will do is integral of A plus bx into dx. This is from A to B. So this comes out to be ax plus bx square by 2 from A to B. It will be AB plus b cube by 2 minus a square minus a square b by 2. This is the work done, right, by this variable force. I am not simplifying it. Now, what did we do in this? We found the work done for a smaller displacement, then we integrated the entire expression. So in general, what we can write here is work done by a variable force is given as integral of f dot ds under certain limits. This is representing the initial position of the particle, and this is representing the final position of the particle, right? And we can also say that work done is nothing but it is area under the force displacement graph. Right? So this is how we find the work done by a variable force. Now let's discuss about types of forces first, based on conservative and non-conservative forces. So let's discuss conservative and non-conservative forces first. Conservative forces. So what are conservative forces? Let me define it for you. Conservative forces are those forces the work done by which in a closed path is equal to 0, or it does not depend on the path followed by the object. So, conservative forces are those forces, the work done by which in a closed path is equal to 0, or it does not depend on the path followed by the object. Right? So, these are conservative forces. Examples of conservative forces is gravitational force, electrostatic force, etc. In this chapter, we will be interested only in gravitational force. Let's take this example to better understand how gravitational force is a conservative force, right? So, this is the floor on which a block of mass m is lying. This is position A for this block. Now this block is taken upwards to this position and say this position is B. The height by which the block has been moved is h. We want to find what is the work done by the gravitational force while we are taking this block from A to B. So this is the point of application of gravitational force. We assume that it acts at the center of mass of the body. This is the displacement of point of application of force, right? This is S vector. So now mg is a constant force, so work done W is given as F dot S vector. We need not have to integrate it, right? So force F is mg minus j caret. We are taking that, or we are assuming that this motion is happening in xy plane. So force is mg minus j caret and S is h plus j caret. So if we take the dot product here, we get work done as minus mgh. Or you can directly write it as Fs cos of 180 degrees, because the angle between the force and displacement is, you can see here, the angle between force and displacement is 180 degrees. So we have work done as minus mgh, and this work done is from A to B. Now when we release this block from here, it falls to the ground, right? So in the second case, the block is moving downwards, so the force is acting downwards, and also the displacement of the block is downwards. You can see here. So now what is the angle between force and displacement? It's 0 degrees. So now the work done from B to A by the gravitational pull of Earth is Fs cos of 0 degrees, or this is plus mgh, right? So now in the closed path, by closed path I mean that we are moving from A to B and we are coming back to A. This is the work done in the closed path, or this is what we understand by closed path. So the net work done in the closed path is WABA is given as work done from A to B plus work done from B to A. This is equal to 0. This proves that since the work done in a closed path is 0, therefore gravitational force is a conservative force. Now let's take one more example. The same example I'll take, but in this case I'll be proving that it does not depend on the path followed by the object. We will now try to prove that work done by gravitational force is a conservative force since it does not depend on the path followed by the object. So let's take this case. This is an inclined plane of angle theta and height h. A block of mass m is kept on the top of the inclined plane. This block starts sliding from this point B to this point C. The forces acting on the block are mg, normal reaction n, and the displacement of the point of application of force is this vector, S vector, right? We learned the definition of work done as force multiplied by the projection of point of displacement of force along the force. So let's see what is the projection of displacement of point of application of force along the force. This is, the red line is indicating the direction of force. The projection of S vector on or along the direction of force is this length. And you can see here that this length is nothing but h, right? So work done in this case is mg into h. We saw that when the object was released at B, it came back to the ground and the distance was h. The work done in this case was mgh, right? So here also the work done is mgh. But in both the cases, the path followed by the particle is different. So please remember that those forces are conservative forces, because of which the work done does not depend on the path followed by the object. Clear? So this is the definition and explanation of conservative forces. Let's learn about non-conservative forces. So, how to define non-conservative forces? It's very simple. If the work done by a force depends on the path followed by the object, then it is a non-conservative force. If the work done by a force depends on the path followed by the object, then it is a non-conservative force. Or you can also say that the work done in a closed path, if it is non-zero, then the force is a non-conservative force. Or if the work done by it in a closed path is not equal to zero, then also the force is a non-conservative force. Now, let's take one example of it. Friction is one such good example of a non-conservative force. Any type of dissipative force is an example of non-conservative force. So let's see how in a round trip the work done is non-zero because of friction. We have this block of mass m. The block is situated at x is equal to 0, and this is position A for this block. This is position B of this block. X is equal to D. What we will do is, we will pull this block along the x-axis or along the plane using some external force F, and we will try to find what is the work done by the friction while we bring this block from A to B and B to A. So for B to A, let's try to see it. From A to B, let's try to find out what is the work done by the friction. So when we are moving this block from A to B, the friction which acts on this block is the kinetic friction, and the coefficient of friction is given to you as mu k, or take it as mu only. So Fk is mu into normal reaction, where normal reaction in this case is mg, right? So Fk is mu times mg. This is the frictional force acting on the block. Now what is the work done from A to B by this frictional force? The force is acting towards negative x-axis. So let's write this as Fk minus I caret dot, the displacement is d I caret. Also we can say that the angle between the force and displacement is 180 degrees, right? This is the displacement S vector. So now we have work done from A to B by the frictional forces given as minus mu mgd. This is WAB. Now, what happens when we pull this block from B to A? Now, when we start pulling this block from B to A, the frictional force will act along this direction. The block is moving along negative x-axis, so the friction will oppose the relative motion of the block, and again it will be equal to mu mg. The angle between the displacement and friction is again 180 degrees, right? So work done by friction when the block moves from B to A is Fk S cos of theta, where theta is 180 degrees, right? So this is minus mu mg into d. This is WBA. So now you can see that work done in the closed path, that is WABA. So ABA is the closed path. The block is moving from A to B to A, is given as work done from A to B plus work done from B to A. So this is minus 2 mu mgd. Now we can see that it is non-zero quantity. So the force is a non-conservative force. So friction is a non-conservative force. Since we have learnt about conservative and non-conservative forces, now let's try to see work done depends on frame of reference or not. So the topic ahead is dependence of work done on the frame of reference. So my question to all of you is, does work done depends on frame of reference? Anybody in the class?
Yes, it depends on frame of reference.
It depends on the frame of reference. Okay, let's check whether the work done depends on the frame of reference or not. I'll take two cases here. So let's try to understand whether the dependence of work done is there on frame of reference or not. Please look at the example on the screen. We have a truck. You can see a truck on the screen, and this is a block which is placed on the truck. The mass of the block is m, and the friction coefficient between the block and the truck is mu. There are two observers. One of the observer is standing on the truck. Say this observer is A, and the other observer is standing on the ground. Say this observer is B. The truck is accelerated with an acceleration A. Now let's try to learn what is the work done by the frictional force when this block is observed from the truck. We will calculate the work done by the friction force as observed by a person standing on the truck and on the ground. So which one of these two observers, that is A and B, is in an inertial frame of reference? Obviously B, right? So this person is in the inertial frame of reference, and this person is in the non-inertial frame of reference. So observer A is on the non-inertial frame of reference and observer B is in the inertial frame of reference. If I draw the free body diagram of this block from inertial frame of reference, let's see what happens. This is the weight mg. This is normal reaction N. And from our knowledge of friction, we can say that friction on this block is acting in the forward direction. Here, friction is helping this block to accelerate in the forward direction, right? So friction F is responsible for the acceleration of this block, therefore F is equal to ma, right? Now, this block is displaced by a distance of d meters. The truck has moved by a distance of d meters in the forward direction. So with respect to this person on the inertial frame of reference, the displacement of the block is d I caret, and the force is ma I caret, right? We are observing this block with respect to B. Please remember it. So we are observing this block from the inertial frame of reference. So work done here is F dot S vector, and this is MAD. So work done from the inertial frame of reference is MTA or MAD in this case, right? Now let's go to non-inertial frame of reference. I will draw the free body diagram of block here. We are observing it with respect to the observer on truck, which is observer A, and A is in non-inertial frame of reference. So the free body diagram is, it looks like this. This is block of mass M. This is weight mg. This is normal reaction N. Friction will act in the forward direction and pseudo force will act in the opposite direction. So this is the pseudo force ma, because as we observe the object from non-inertial frame of reference, an additional force has to be added in the free body diagram, and that is the pseudo force to apply Newton's laws of motion. So now here, with respect to A, block is at rest, right? So F minus ma is equal to 0. So force F is ma. Now what is the work done? Since the displacement of point of application of force in this case is 0, therefore work done is F into 0, which is 0. Now, what is the inference which we draw from this discussion? We saw that the force of friction was ma in either of the cases. The real force will not change, right? But when we observe the work done from this force from inertial and non-inertial frame of references, the answers were different. From inertial frame of reference, the answer was MED. And from non-inertial frame of reference, the answer is 0. So since the work done by the same force in two different frame of references is different, therefore we say that work done does not depends on the frame of reference. So the inference which we draw is work done does not depends on the frame of reference, right? So in this session, we have learnt about the definition, the basic definition of work done. You saw what is the displacement in work done. It is the displacement of point of application of the force, right? We saw what is conservative and non-conservative forces. We learnt about the dependence of work done on the frame of reference. Thank you very much.